In this video, we will look at another service provided by the data link layer, that of reliable data transfer. But first, a quiz. Where are we placed right now? We saw that the role of the data link layer is frame by frame next hop delivery. And when frames get passed over a link, they can get corrupted. At times, they can even get lost. And we saw that error detection is a mechanism that can help detect corrupted frames. Error correction can also help, but in some cases when there are too many errors, there is not much that can be done. So what do you do next once that you have detected that your frame is bad or you didn't even receive a frame, where frame is lost? Naturally, when frames are corrupted or lost, a lot of applications don't like it. So you want to provide a reliable data transfer. So the job of this reliable data transfer protocol is to recover from these corrupted or lost frames. And this is one of the most researched problems in networking. Reliability as such is handled both at the link layer as well as the transport layer. Providing reliability at link layer is a lot simpler than that at transport layer. So at link layer, we will develop the framework for providing reliable data transfer and we will extend it as part of the transport layer. So here is the outline for this video. In this video, we will develop a reliable data transfer protocol. So this protocol provides a reliable channel service to the higher layers. So as far as the higher layers are concerned, they send the data and to them it looks as if they are sending the data over a reliable channel. So they don't have to do anything about it. But in implementation, what happens is they are sending the data which is being handled by this reliable data transfer protocol, which is in turn operating over an unreliable channel, but it is giving an impression of a reliable channel to the higher layer while it is operating over an unreliable channel. So what we will do here is we will start out with an unreliable channel with bit errors only and then slowly add losses on top of it and we will incrementally build the reliable data transfer protocol. So first we will look at a channel with bit errors. What this means is the packet can get corrupted but not lost. In other words, you will receive the packet, but it can have some bit errors as part of it. We saw that we need some functionality. So what we are going to do here is list the functionality that is needed to provide reliable data transfer. So one functionality we will definitely need is error detection mechanism to determine whether the frame or packet is corrupted or not. This we have seen is achieved through checksum CRC and so on and so forth. What else do we need to provide reliable data transfer? So let me take the telephone analogy. Suppose you're talking over a noisy telephone line with someone. How do you ensure as a speaker that whatever you speak is actually being received by the other user? That is, how do you ensure reliability over a noisy telephone line? What human protocol do you use? So basically, the receiver is going to provide you feedback. And there are two types of feedback. Positive feedback. So basically the receiver says, aha, oh, acha, okay, This is positive feedback in the form of ak. There is also negative feedback. In other words, the receiver did not hear what you said properly. He can tell something like, repeat that, I didn't follow, what did you say, so on and so forth. This is a negative feedback. So N stands for negative, negative acknowledgement. This is positive acknowledgement. Now, do we really need both? Now you may be tempted to say that negative feedback alone will suffice. You don't really need positive feedback. In other words, if I'm not saying anything negative, assume that I'm receiving everything all right. Suppose your mother is nagging you about something you're supposed to do and you didn't do, and this is over phone, and you just keep the phone down and walk away. Now, does your mother have a way of knowing that whatever she's saying is actually getting into your head? No, right? So you have not really achieved reliability. What it translates to here is if the other system kind of crashes, then you think as a sender you're sending this packet, the other system has crashed, so it is not providing you any feedback. Thereby you're thinking that everything is all right, but in fact whatever you're sending is not being received by the other node. So we will address this issue of NAC versus ACK or NAC and ACK later in detail. But for now, let's assume that the feedback, the receiver feedback, is both in terms of ACK and NAC. So if the sender receives an ACK, he is going to send the next packet. So what should the sender do when he receives an ACK? That's right, he has to retransmit the previous packet. So the required functionality now so far boils down to this. We need error detection mechanisms. We also need a receiver feedback. For now, we are considering both ACK and NAC. Now, protocols based on this feedback and retransmission mechanism are called automatic repeat requests. They are called ARQ protocols. So here is our first version of reliable data transfer protocol in action. So you send a packet. When you receive an ACK, you send the next packet. On the other hand, if you send a packet and some bits are corrupted as represented by this, the receiver sends a NAC, and on receipt of the NAC, you resend the same packet because you realize that this packet is corrupted, so you're going to resend the same packet. So is this functionality adequate to provide reliability? What if the ACK or NAC got corrupted, in which case the sender has no idea on the feedback. It doesn't know whether the feedback is positive or negative. Now what should the sender do then? So if the designer is an optimist, he can just assume that the corrupted packet is an ACK and just send the next packet. But what if the previous packet was lost? Then your RDT protocol is not providing reliability. If you could also be a pessimist and assume that even though the previous packet is an ACK, it could have also been an ACK and thereby retransmit the previous packet. Now what is the problem with this? If the previous packet is indeed not lost, now you are sending duplicate packets to the receiver. Our goal is to provide reliability, thereby this cannot happen. You need to assume the worst and send the previous packet. So now this retransmitting packet, previous packet, can potentially create duplicates. So how do you handle these duplicates at the receiver? In other words, what functionality do you need to overcome duplicates? Right, you need to now sequence the packets, the data packets that is. So here is a summary of RDT version 2. So the receiver provides feedback in the form of ACK and NAC. Now sender retransmits a sequenced packet on NAC or a garbled ACK or NAC. Now the receiver discards duplicates, if any, based on the sequence number because it remembers the previous sequence number, and if it sees the same sequence number again, it knows it's a duplicate, thereby it will discard it. So up till now we saw that we need three mechanisms: error detection, receiver feedback and data sequence numbers. Now that we are dealing with sequence numbers, an important question to ask here is, what is the sequence number space? By what do I mean by this? Basically, the minimum number of sequence numbers you need to get the protocol in operation. In other words, do you need sequence numbers starting from 0 all the way till infinity, or can you manage with just 0, 1, 2, 3, or can you manage just with 0, 1 and so on and so forth? So how many sequence numbers do you need to make this protocol work? So just two sequence numbers 0 and 1 will suffice. This basically means one bit which carries the value either 0 or 1 will suffice for RDT version 2. Why? At the receiver, suppose it has some packet, all it needs to know is whether the next packet is the same as this or the next packet is different from this. This distinction can happen based on just two sequence numbers. So here is RDT version 2 in action. So you sent a packet, it reached fine, ACK also reached fine, you move on to the next packet. In this case, you sent a packet but it got corrupted, thereby you are sending a negative acknowledgement. Because of this, you are resending the packet. In this case, you send the packet but the ACK got corrupted, so the sender now doesn't know whether the previous packet reached correctly or not. To be safe, you are going to retransmit the packet, but you are using the same sequence number as before. Since the receiver already received packet 0 before, it's going to view this as a duplicate and it is going to discard it. Now here is a case where the packet got corrupted, thereby the receiver generated a NAK, but the NAK also got corrupted, in which case you are again resending the previous packet. Now the receiver accepts it because it didn't get the previous packet correctly, I mean. So as far as channels with bit errors are concerned, are you convinced that RDT version 2 handles everything? In other words, there are no flaws as part of this particular protocol. Actually, it does. We have covered all possible combinations and handled it. But now I'm going to look at an optimization of this protocol. So I'm going to work with version 2.1. So what is this optimization? I don't want to use two types of packets, ACK and NAK at the receiver. I want to get rid of these NAKs. In other words, I want to go for a NAK-free operation. So the question here is, can you convey the same information as a NAK but through a NAK? How would you do it? So here is the answer. So instead of sending a NAK, what the receiver can do is it can send an ACK of the last correctly received packet. In this case, because it is ACKing some last correctly received packet, it needs to include the sequence number of packet being ACKed. Until now, the ACKs we have seen in other versions until 2 did not carry any sequence number, but here on they need to carry the sequence number of packets being ACKed. Now what does the sender do? Now if the sender sees a duplicate ACK, it can interpret it as a NAK and retransmit the current packet. So here it is in action. You send packet 0, it received fine. You send packet 1 and it got corrupted. So ideally earlier you would have generated a NAK, but what are you doing here is you are resending the ACK of the previous correctly received packet. Now it has already seen ACK 0 and it is again seeing ACK 0. This duplicate ACK is interpreted as a NAK and thereby you are going to retransmit the previous packet, which is packet 1. So dwell on it a bit and convince yourself completely that this indeed works. So in our optimized version, we need the error detection mechanism. We need receiver feedback, but now we are just relying on ACKs and we need data sequence numbers. But since we are relying just on ACKs, now the ACK carries sequence number of data packets. So far, we have considered a channel with just bit errors, and we started with just error detection and built upon it and added these 3 other functionalities. Now we will move on to channel with errors as well as losses.